Welcome to today's webinar with the title Experience the Flexibility Physical PCB Sample WE.flexone. I am Andreas Schirp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik Circuit Board Technology, Würth Elektronik from our Technical Project Management. Welcome back, Werner. I now wish you lots of fun and new information.
Thank you, Andreas. So, also welcome from my side to our webinar regarding our physical PCB sample FlexOne. First, I would like to introduce myself. My name is Würth Elektronik and I work at Würth Elektronik in the technical project management. So my daily business is we get special, I would say a little bit special customer requests, mainly in the flex rigid technology. And we are looking for this, and also we are taking care for the production of such PCBs. I'm now already since 2002 at Würth Elektronik, and I would like to present today our new PCB sample WE.flexone. First, the presentation of the sample itself. Then I would like to look a little bit deeper inside, mainly the Stackup. We will speak about flexible solder mask versus coverlay. So what is the difference? We speak about signal integrity. How can I do this? We've got a part regarding sieve contacts and LiftOff technology, really interesting part. And the point 6 is the combination with the HDI technology. How can I combine flex rigid and HDI technology? And the last point is regarding the QR code on the PCB. So this is the agenda. Now I would like to show you the sample here in my hands. You could see here on the right side, it's now the 2-layer flex part, so 2F XRI part. Top layer signals. On the bottom layer we have the ground layer, partly full copper and also partly hedged. On the right side you could already see the different flex stripes. We have the 1-layer flex part with the lift off of the sieve and this other contact here. Perfect. Good. We come back to the presentation. First, you could see here both sides of the PCB. Top side where the flex signals are running, and the bottom side where only, I would say only the rigid parts are. You could see already a difference in the color. So you could see here, I could make it a little bit bigger. You could see here the flex parts have a dark gray solder mask. It's a flexible solder mask. Everywhere where's a flexible part, flexible solder mask. And you can see the rigid parts with our standard solder mask. It's from the top side and the bottom side. It's the same solder mask, but as you can see, we have another color. It's only because the material under, we feel the material, the polyamide material under. So the polyamide is an brown material, so it's a little bit more dark. And here under we have the FO4 material, so it's a little bit more bright, but it's the same solder mask in the rigid parts. Good. What are the points we would like to speak about? As I said, we are beginning with the Stackup itself, with flexible solder mask coverlay. I would like to introduce the sample. We have the part with the signal integrity on the left side, with the 2-layer flex part, on the right side with the 1 copper layer in the flexible area. And the point I said regarding the sieve contact and the lift-off areas we have introduced into the sample. The combination with the HDI technology, in this case a BGA with 0.4mm pitch. And the last point is regarding the QR code, which is on the bottom side of the sample. Good, we start with the Stackup. What is the main difference between both samples? On the left side we have the 2F XRI samples, and the right side we have the 1F XRI sample. Main difference, one layer, copper layer on the flex area, combined with the other flex part, which has two copper layers in the flex area. Both flexible areas have a width of 10 millimeters, so if you have the samples in your hand, you can test the bendability of the PCB itself. From thickness of both, if you are using a standard stack of Würth Elektronics, so with one layer in the flex part, we roughly have a thickness of the flexible material of 120 micron. At the 2F part, we have roughly a thickness of 190 micron because of the 2 times copper and the 2 times flex mask and coverlay in the flex area. From bending issues, in general, we recommend as Würth Elektronics, it's also according to the IPC, to have as the min bend radius 10 times the thickness of the flexible area. That means 1.2 millimeter min bend radius, and here roughly 1.9 millimeter bend radius for flex to install applications. So, difference, what we have, standard, if you don't have a request, we are always putting a flexible solder mask outside on the flexible area. Option, coverlay, also possible on the outer layer. Coverlay instead, it's a polyamide full with an acrylic or an epoxy glue, which is laminated on the outer layer. So both for the protection of the signals in the flex area. If I look on the left side with the 2-layer flex outside, on the outer layer, standard is also here a flexible solder mask, but option also coverlay on the outer layer possible. If I look on the inner layer, so the layer 2 on the flexible part, I always have to use a coverlay. That means the polyamide foil, because I cannot print a flexible solder mask into this cavity here. So this is the main difference between both samples. We are now looking a little bit deeper into the production process of the samples. Here now the process steps of an 8-layer PCB. In this case 8 layers in the rigid part and 1 layer is crossing over the flexible area. That means 1F7RI stack. As you can see on the colors, the brown one are flex specific production steps, and the rest of the steps here are standard multi-layer processes. As you can see, we have 3 inner layer cores in this case, 1, 2, 3. Special is only the core directly under the polyamide material. We have small V grooves directly at the flex rigid intersection. So it's here mentioned, yeah. Why we need this, we come back later. The other point is the low flow prepreg, which we are using for flex rigid boards. The flex rigid is always in between this core and the polyamide material itself, and we are doing a window milling directly there, where we don't want to glue the polyamide material on the FR4 material. So difference between a low flow and a standard prepreg is only that the resin don't has this flow anymore. Then we come to the multi-layer pressing, multi-layer laying and pressing. Then we come to the point, as I mentioned, flexible solder mask on the outer layer, and at the end depth milling process. To show it a little bit more detailed, I've got here on the right side the different processes. Always the core underneath the polyamide material. We are doing this small V groove directly at the flex rigid intersection. We have the low flow prepreg, where we mill this window inside where the later flex part is. Then on the top side we have a copper laminated polyamide foil, which we are already purchasing like this of our supplier. And on the back side with a standard pre-preg and a copper foil. This we press together, and as you can see now, we have here now a small gap where the pre-preg is missing. This is the later flex area. Now all the processes which are following, like the drilling, the etching, the plating, solder mask, are done like at a rigid multi-layer board. So it's a stable production panel. As you can see here, the flexible area, we have in the rigid parts the standard solder mask, and the flex area this flexible solder mask, which is overlapping at the intersection. Okay, if we are now doing this depth milling at the end, because of this we also need this small V-grooving, because we've got only here a gap of 50 micron between the polyamide and the core. So, and we don't want to mill inside the polyamide, or we don't want to hurt the polyamide. We have the small V-grooves, so we only have to do the depth milling until the V-groove beginning here. So that means depth milling, and if I now mill the contour of the PCB, the rigid material under, which is not glued to the polyamide material, is falling out, and I've got my finished flex rigid PCB. This is for the 1F XRI technology. If now I have the 2 layers flex outside, it's a little bit different. You could see here, now I have a polyamide core with 2 copper layers in the flexible area. First I do the imaging of the inner layer, then I have a coverlay like mentioned here. You can see here with this brown color, also overlapping here roughly 1 millimeter into the rigid area, and this is laying and laminated to this flex area. Also like the flexible solder mask, partial only in the flexible area. The same here, I need the core underneath with this V-scoring, I need the low flow pre-preg, and the multi-layer lamination, everything at the end is the same with the depth milling and so on. So additional process what we have to do an inner layer process for the polyamide core, and we have to add this cover layer foil, which is always a manual process on the inner layer of the flex. To show it a little bit deeper, flexible solder mask and cover lay. On the left side you could see a production panel. The flexible solder mask is a completely automated application using the inkjet technology. I've got here a small video for it. You could see here the production panel. Already the rigid solder mask over it, we are doing a pre-cleaning. The brown area is now the flexible areas with the copper structures in the flexible area. Now it comes into the inkjet machine. We are doing a registration over the fiducials and printing now partial the flexible solder mask in the flexible areas. I will now go on a little bit because it takes 1 minute and 40 roughly until the panels now come out. And as you can see now, the flexible areas with the dark gray color are now covered with the flexible solder mask. Here now a cross section. You can see here the polyamide material. You can see the copper structures in the flex area and the flexible solder mask, which is now covering the different areas. Here you could see rigid parts, the flexible parts here in between. Good. On the right side, we could see the cover lay. So cover lay is always, as I said, a manual process. We first have to cut this cover lay foil. We have to fix it and to press it with here now vacuum lamination machine, partial on the flexible area. So main difference, automated process, flexible solder mask. It's also our standard process, but cover lay is always possible. The main differences are listed here. I will not go now any more deeper inside. There's also a link here for a webinar which I hold for the differences in between flexible solder mask and coverlay. There you could read about what are the main differences between both variants. Good. So we go on with this point: signal integrity. Left side 2-layer flex, right side 1-layer flex. So the main advantage if I'm using the flex outside for signal integrity is the one-to-one transmission of the signals. So we don't need any vias and in this case jumps of the impedances. Yeah, as you can see here in the sample, I've got a connector and we can go one-to-one by the lines on the same layer across the flex part to the other rigid part. Ground layer, in this case, we could use as layer 2, but we could also turn it that we do the ground layer on top and putting the signals by microvias to the inner layer. You could see here now the cross sections of 2 microvias. Here now with a non-copper filled microvia, here now with a copper filled microvia. If it's sitting directly in solder pads, we should fill them by copper to have a planar surface at the end. Polyimide material and the layer 2. Here you could see the model, edge couple coated microstrip model with a differential pair and a reference plane on layer 2. And always a question we are getting: how should we do the hatch plane? Should it be hatched, or the reference plane I said, sorry. Should it be hatched or should it be a solid plane? In general, for the signals, we recommend a solid plane because then like this we have the best signal behavior. So why not doing a compromise of both? That we have directly under the differential pairs in this case, we have a full copper, here now with the green color, and all other areas are hatched from the ground plane. Because hatching has advantages for the drying of the PCBs prior to the soldering processes, and at the end we are getting more flexibility here. Yeah? So this is a compromise. Another thing for the hatch is if I'm doing a hatch directly under differential pairs, I could maybe use a thinner polyimide because the impedance goes up. The behavior of the signal, yeah, it goes down at the end. For the 1F sample, it's the same. Also, main advantage is the one-to-one transmission of the signals directly from one to the other part. We could see this here on this right upper part. We've got here now a model with a coated coplanar strip. That means we have here a 50 ohm single-ended line with the reference planes on the left, on the right side, and no additional ground plane on layer 2. So it's always dependent what requests you have on your PCB. So both variants are possible with impedance defined lines. Good. This regarding signal integrity. Now we come to the point sieve contacts plus lift-off areas. Sieve contact means zero insertion force, means a detachable and cost-effective connection of two PCBs maybe, always used or often used if you have modular systems. Such sieve contacts have low construction heights and are connected on the one side by a FFC, a ribbon cable, which you can buy in a catalog, or you have customized flex or RIGID.flex PCB, so-called FPC. You could see here from our sample, the top side, flex part coming here, and here the contacts of the sieve. The back side looks like this. We have here a full rigid part, which is depth milled to the remaining thickness of normally 0.3 millimeter, like it's specified in the sieve connector datasheet. You could also see here in our sieve contact in the sample, we have here two ears. It's only for better handling, for introducing it into the connector itself. It's a could have on the sample. So to go a little bit deeper inside, We have a lot of similarities for the SIF contacts. You could see here 3 connector types with such ears, without ears. So the similarities are always, we have small contour tolerances. You could see here, plus minus 50 micron, plus minus 50 micron. We also have small tolerances from the contacts to the contour of the PCB, like you see here, plus minus 70 micron, plus minus 17 micron in this case. And we have small radius for the interlocks. So here, like a radius of 0.2 millimeters. So what is the consequence for our production? We know that such tolerances and radius, it's not anymore possible via a milling process. That means we are always, or we are generally cutting such SIF contacts by a laser process. So you could see it here. It's a picosecond laser where we are cutting the flexible material. So main advantage is the registration of the laser via the conductive pattern. So we have fiducials for the registration. So the tolerances from contacts to the contour and also the contour itself, we don't have any more problems. What we are doing a connection to the delivery panel. So mainly we are also laser cutting the attached flexible part, and we are connecting the flex plus the SIF part by small tabs, micro bridges to the delivery panel, that you don't get any problems in your assembly process, that the SIF is coming up or something else. This can afterwards only be taken off, these small bridges, so you don't need any scissor or something else to cut these bridges. Some more points. The delivery panel becomes more stable. You can see here the FR4 material under this LiftOff or SIF area is remaining, and we also could have an optimized delivery panel like here, because we don't need this big milling diameter, for example 2 millimeter milling tool. We only have the small laser cut line with a width of 30 to 50 micron. So the PCBs or the flex parts can be, we don't need that much distance in between these parts. Okay, now we come to the differences. So where we as the PCB supplier often get problems. So this is a standard tolerance, like we say, plus minus 50 micron, perfect for our production. Plus minus 30 micron, still possible, but we need, it's an advanced requirement. Yeah, this is mainly for SIF connectors, maybe with a pitch of 0.5 millimeter or smaller. The tolerances of the thickness are getting smaller. This here is a no-go. Yeah, such a tolerance of 0.29 to 0.34 millimeter, we cannot produce such a SIF contact anymore. So what are the consequences? Means if you are choosing a SIF contact with this highest tolerance of plus minus 50 micron, we could use our standard process with depth milling. If we have this plus minus 30 micron, we have to use a polyimide stiffener. You will see it later. And if we have such a tolerances, we have to say our PCB is not matching with your SIF connector. So such a tolerance is only made for ribbon cables, because they don't have such tolerances like we in our PCB production with the galvanic copper, with the surface, with the pressing process and so on. So it is only for catalog ribbon cables mentioned. So differences, FR4 stiffener, as I said, automated depth milling process, tolerance is plus minus 50 micron, so best in costs. On the right side we have the polyimide stiffener. You could see here, it's also a thick coverlay material which we have to lay in manual in the multi-layer lamination process. So it's always a manual effort, so the PCB itself gets more expensive. So our recommendation is, so search the right SIF connector at the beginning of your project with the right tolerances. If you are not sure, contact us, we can help you. Okay, to go on, LiftOff area, you could see here the flat panel, the long flex part and the other one. which are already here released of the unglued FR4 material. So one advantage is we could use here the inner layers, also the bottom layer for routing and assembly. So we don't need any space here. What is also often used is LiftOff technology. I will make it a little bit bigger. You could see here that we are doing this LiftOff, that the flex is not going until the end of the rigid part, that we are removing already the flex area 5 or 10 millimeters before we come to the end. This is often used if I have maybe a housing or something which is at the end of this rigid part and we cannot go out directly here with the flex. So from production process, it's really easy. We only have to do a bigger window milling for the pre-break, so it's not more effort. What we always recommend, if you have a lift-off area, we are not doing this with a milling or depth milling process. You could see here this blue color. We are still doing this with a laser process, to cut the flex material itself. One more advantage of this lift-off we could see here. It's a dynamic application for, I think, 5 to 10 million bending cycles. It's now a 2-layer flex, as you can see here, polyamide with 2 copper layers in the flex area, but we have, where the bending area is, only 1 copper layer on layer 2 remaining. Because for dynamic bending issues, we don't want to have this outer layer on the flex area, because in the outer layer we always have this galvanic copper of the plating from the vias, and so we also have this on the surface. So better is to have this layer 2 only. There we have only the base copper. We could use here such an RA copper, rolled annealed copper. It's a better copper for dynamic bending instead of this electric or ED copper at the end. What we have covered here, we've covered with a coverlay and this lift-off, as you can see here. This one is the lift-off area on both sides. This is the rolling direction of this flex. This lift-off supports this rolling movement directly. So the flex cannot go down here anywhere. So the movement of this rolling direction is always the same. You could see here, lift-off area, the FR4 under, and here's the gap. Here's the small V-groove, as we said at the beginning, which we also need when there's a lift-off area. Good. Lift-off SIF area. Now we come to the combination with HDI technology. In this case, we have a BGA with an 0.4 millimeter pitch on the PCB. In general, I would like to mention if you have a combination between flex rigid and HDI, so if it's only micro vias, it's okay, but if it's going micro via, buried via, stacked micro via, please contact us, because we cannot combine our HDI design rules with the flex rigid technology one-in-one. So here in this case, BGA 0.4 millimeter pitch, micro via pentameter solder mask, clearance plus web, as you can see here. Here's a small picture, BGA 0.8, BGA 0.4 millimeter, only difference in the size of such a BGA. The cross sections here are now, as you can see, one milled with, it's now the 2-layer flex material, so the polyamide here in between. Top layer with the additional galvanic process, like I said, and the layer 2 as maybe here the reference layer. You can see here diameter of this microvia only 100 micron in this case, and it's here in this case a 75 micron thick polyamide which is used. Double-sided flex. On the left side picture you could see it's an 1F XRI PCB, because polyamide 50 micron in this case, and we have once again this 50 micron no-flow pre-break here inside. drilling diameter, here now 125 micron. And as you can see here, here's once again an bird via or a second micro via from layer 2, because here you could see the several plating processes on this layer, which are also then in this via next to. Good combination in general for 1F XRI. If you're using a standard stack, micro vias, both sides can always be combined with our standard stack. If you have bird vias, we have to look for a little bit more, I would say, special stack, because in this case we need first the pressing from layer 2 to layer 5 here, drilling the bird via, do the plating, and then we are pressing the low flow prepreg plus the polyamide on it. So if you have more than this, contact us, we could help you regarding the stack up. If I have now a 2-layer flex outside, it's getting a little bit more difficult. So micro vias are still possible with our standard stack, but if you need now a bird via or a micro via from layer 2 to layer 3, it's no more possible. The reason is we are having here a double-sided flex material, polyamide 2 times copper, and we cannot begin with an drilling here. So we would need a special stack like on the right side. So we are first producing, in this case, a 1F 5RI PCB, so polyamide, low flow prepreg, pressed together, and then we are putting once again a prepreg and an additional 1F polyamide fall on top. So in this case also 2F 6RI, but we are getting much thicker on this area because we have now 2 times this polyamide inside with 2 times copper with plating inside. So we are getting here roughly, I would say, up to 300 microns thick. So in this case, it's always the question, maybe it makes more sense to put the flex in the middle of the PCB. But this we need to discuss for each project several. In general, I only would like to mention, so as you have seen, we have different VR technologies in combination with different stack-ups. So is the polyamide outside, polyamide in the middle? Do I have stacked micro vias or stack-out micro vias, micro via bird via, filled and capped via? So we cannot combine flex rigid in HDI design rules 1 and 1. And our recommendation is always, if you have a little bit more complex PCB, contact us. So it's our job here to help you to find the right stack for your application. Good. We come to the last slides. QR code. Here's some more information. We've got also a flyer on our homepage. So different code types. We could do DMC, QR code, barcode, or also text on the PCB. Yeah? This could also be done for traceability of the PCB. We can have the number of the production panel, of delivery panel, single PCB, serial numbers. So everything is possible. This we are also doing by an inkjet print process with a white color. Yeah. So this QR code on the PCB itself, there's a link to our homepage. Then you come here. There's once again an explanation of our physical PCB sample, where different parts mentioned like the coating, the outline, mechatronic, signal integrity, sieve contact, so everything mentioned once again. And also the main thing, I cannot find now. So you could also order this physical sample here, but the red box below. Yeah. Order physical sample now, yeah. If you are clicking here, I think we've got here a small bug inside, so we will concern for this. This we will look for afterwards. Good, come back to the presentation. So for the link, we will look once again. We are at the end. So thank you for your attention.